You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we step into a Berlin lecture hall at the turn of a century, where physics feels complete, almost smugly so. The great classical systems have been built. Newton has ruled the motions of the heavens and the fall of apples for more than 200 years. Maxwell has written the laws of the electromagnetic field. Thermodynamics has given industry a grammar of heat and work. There are still details to polish, of course, but the structure seems sound. Many physicists speak as if the book is nearly finished. And then there is a small problem with light and heat. The kind of problem that looks minor until it refuses to go away. It appears when you try to describe how objects glow. If you heat iron, it reddens. Heat it more, it brightens, and the color shifts. A stove coil glows orange. The sun glows white. Every warm body emits radiation. Physicists could measure this radiation with increasing precision, and by the late 19th century, they had a name for an idealized emitter: a blackbody, a perfectly absorbing object that, when heated, emits radiation in a way that depends only on temperature, not on composition. A blackbody is a clean theoretical object, and nature provides approximations. A cavity with a small hole behaves like one, because light entering bounces around and is absorbed, and light emitted emerges as if from a perfect source. The measurements of blackbody radiation were extraordinarily accurate. The problem was the theory. Classical physics could not reproduce the curve. Enter Max Planck, a man who did not want to overthrow physics. He wanted to preserve it. Planck was born in 1858 in Kiel, in what was then part of the German Confederation, into a family steeped in education, law, and theology. He grew up with discipline, music, and seriousness. He was a gifted pianist and considered music as a possible life path. But he chose physics because it offered something he craved: a sense of deep order, a lawfulness that felt moral. Planck's temperament was conservative in the intellectual sense. He admired the idea of absolute principles. He distrusted speculative leaps. He wanted the universe to be coherent, and he wanted humans to be able to know that coherence. When he studied physics as a young man, he was warned, famously, that physics was essentially complete, that there was little left to discover. The story is often told as if Planck ignored this advice and dove into the unknown anyway. But the truth is subtler. Planck did not enter physics with a hunger for novelty. He entered with a desire to understand the existing laws more deeply, especially the second law of thermodynamics and the concept of entropy. Entropy fascinated him because it seemed like a law with teeth. It was not just a convenient principle, it felt irreversible, like time itself. Planck became an early champion of thermodynamics and attempted to ground it in fundamental reasoning. He was initially skeptical of Ludwig Boltzmann's statistical interpretation of entropy, because Boltzmann's approach suggested that macroscopic laws arise from probabilities, not absolutes. Planck wanted certainty, and probability felt like a concession. That is important to remember, because the quantum revolution begins as a concession. By the 1890s, Planck was a professor in Berlin, respected and established. He was not a showman. He was known for clarity, for seriousness, for a kind of intellectual integrity that made colleagues trust him, even when they disagreed. He was also a man of routine and duty. His life from the outside looked stable. Inside, like many lives, it was shaped by pressures and losses. Personal tragedies would come later, including the deaths of children and the shadow of war. But at this moment, around 1900, Planck is a physicist facing a stubborn curve. The curve is the spectral distribution of blackbody radiation. How much energy is emitted at each frequency for a given temperature? Experiments showed a peak that shifts with temperature and then falls off at high frequencies. Classical attempts to derive this distribution failed in a catastrophic way. One classical approach, using ideas about energy equipartition, how energy should be shared equally among modes, predicts that as frequency increases, the energy emitted should also increase without bound. That would mean a blackbody emits infinite energy in the ultraviolet and beyond. It is absurd. It became known later as the ultraviolet catastrophe. The phrase makes it sound dramatic, and it is, but the catastrophe is not merely that a formula is wrong. It's that the foundation beneath the formula, the assumption that energy is continuous and can be divided without limit, seems implicated. Physicists tried ad hoc fixes. Wilhelm Wien proposed a law that matched data at high frequencies but failed at low frequencies. Lord Rayleigh and James Jeans produced a law that matched low frequencies but diverged disastrously at high. The curve was mocking the theory. It was as if nature were saying, you can use your old tools to describe one end or the other, but you cannot use them to describe the whole. Planck set himself the task of finding a formula that matched the full curve. At first, he treated it as a problem of thermodynamics and electromagnetism. He modeled the walls of the blackbody cavity as containing oscillators, tiny charged systems that could emit and absorb radiation. If he could describe how these oscillators exchanged energy with the field, he might derive the distribution. He pursued this with the methods he trusted: classical reasoning, entropy, and the idea that the second law must be obeyed. His early attempts produced partial results, but the experimental data were too precise and too unforgiving. By late 1900, Planck found himself in an unusual position. He had an empirical formula that fit the data, but he lacked a theoretical derivation that satisfied him. For a man who valued principles, that was intolerable. So he did something he later described as an act of desperation, not because it felt metaphysically right, but because it made the math work. He assumed that the oscillators in the cavity could not exchange energy continuously, but only in discrete packets. The energy could change by integer multiples of a basic unit, E equals h nu, where nu is the frequency and h is a constant. That constant, now known as Planck's constant, is one of the most important numbers in physics. But in 1900, it was simply a parameter that made the curve behave. This is the strange birth of quantum theory, not as a philosophical declaration that nature is discrete, but as a mathematical trick used by a conservative physicist trying to save classical physics from embarrassment. Planck's quantization assumption allowed him to count the number of ways energy could be distributed among oscillators, an explicitly statistical move that forced him, ironically, closer to Boltzmann's methods than he had been comfortable with. By treating energy as composed of discrete units, he derived the Planck radiation law, which matched experimental data across the spectrum. The ultraviolet catastrophe vanished. The curve was explained. On December 14, 1900, Planck presented his results to the German Physical Society. It is often marked as the birth date of quantum theory. Yet Planck himself did not celebrate it as a revolution. He saw it as a formal step, a convenient hypothesis. He thought, or hoped, that the quantization might be an artifact of the interaction between matter and radiation, not a statement about reality itself. He did not yet see that he had opened a door that could not be closed. What does it mean to say energy comes in packets? It means the smooth continuity of classical physics is broken at the smallest scales. It means you cannot assume you can take any amount of energy, divide it into any fraction, and apply calculus as if nature were infinitely divisible. It suggests that at the microscopic level, change happens in jumps. That is not merely a technical adjustment, that is a different universe. Yet for several years, quantum theory remained a strange corner of physics, a useful formula with unclear meaning. Many physicists treated Planck's quantization as a mathematical device. Planck himself tried repeatedly to derive his law without relying on true discreteness. He was uneasy with the implications. He had, in a sense, created a child he did not fully want. Then Albert Einstein arrived and treated Planck's quanta as real. In 1905, Einstein proposed that light itself comes in discrete packets, later called photons, to explain the photoelectric effect, where light ejects electrons from metal in a way that depends on frequency, not intensity. This was bolder than Planck's original step, because it suggested quantization was not just a property of matter's oscillators, but of the electromagnetic field itself. Planck surprisingly supported Einstein's career and recognized his talent, even if he did not immediately accept the photon concept. Planck was conservative, but he was not petty. He could recognize genius even when it threatened his worldview. Over the next decades, quantum theory grew through the work of many minds: Bohr, Heisenberg, Schrödinger, Born, and others. Planck watched as the implication of his constant spread into atomic spectra, chemical bonds, and the structure of matter. He watched as classical determinism gave way to probabilities, as measurement itself became entangled with what could be said about reality. He watched, and he struggled. Meanwhile, was marked by deep sorrow. He married Marie Merck in 1887. They had children. Marie died in 1909. Planck remarried and continued working, but tragedy did not leave him alone. Two of his daughters died, one in childbirth, another in wartime circumstances. The First World War and then the rise of the Nazi regime dragged Germany into darkness. Planck was a patriot in the cultural sense, devoted to German intellectual life, but he was not a Nazi. He tried, with limited power, to protect scientific institutions and Jewish colleagues. His position was painful. He wanted to preserve the fabric of German science, yet the regime was tearing that fabric apart. The most devastating blow came through his son, Erwin. In 1944, Erwin Planck was implicated in the July 20th plot to assassinate Hitler. He was arrested, tried, and executed in 1945. Max Planck, by then an elderly man, endured the kind of grief that makes the idea of cosmic order feel like mockery. His home was destroyed by bombing. Much of his life's work and personal archive were lost. He died in 1947, having lived long enough to see both the triumph of quantum theory and the collapse of the world he had known. So why call him the reluctant father of the quantum? He did not set out to start a revolution, only to solve a problem. And he solved it with a step so small, it initially looked like a technical choice. History is full of revolutions that began as technical choices. Planck's constant turned out to be a boundary line in nature. On one side is the classical world, where objects have definite positions and velocities, and where energy flows smoothly. On the other is the quantum world, where energy comes in quanta, where atoms have discrete spectra, where particles behave like waves and waves behave like particles, where certainty has a floor. Planck's story is also a reminder that science is not just a parade of bold personalities. Sometimes the key step is made by someone who doesn't want to be bold, by someone who is careful enough to see that the old rules do not fit, and honest enough to admit it. Planck did not cling to classical physics out of pride. He clung to it because he believed it was close to truth. When truth demanded a new assumption, he made it. He did not like the implication, but he did not deny the evidence. Picture Planck, late in 1900, staring at the data and at his equations, feeling the discomfort of inconsistency. Imagine a man who has built his intellectual life on the idea that nature is continuous, that change is smooth, that the calculus invented for a continuous world is the right language for reality. Now imagine him realizing that the only way to make the curve behave is to treat energy as if it comes in discrete packets. It's not triumph he feels first. It is relief mixed with unease. The equation works, but the cost is conceptual. He has paid the cost because the universe demanded it. And then in the years after, he watches others take that small step and sprint with it. He watches Einstein turn quanta into photons. He watches Bohr quantize orbits. He watches the younger generation build a physics that no longer pretends the world is fully knowable in the old sense. He watches the new physics conquer atoms, chemistry, and technology, while he himself remains emotionally anchored to an older ideal of certainty. That tension between what he discovered and what he wanted to be true is the human drama at the heart of his scientific legacy. Planck's constant is now written everywhere in physics. It appears in the uncertainty principle. It appears in the Schrödinger equation. It appears in the quantization of energy levels and angular momentum. It is a measure of how grainy the world is at small scales. When H is effectively negligible, classical physics works. When H matters, the quantum world asserts itself. The constant is like a watermark on reality, invisible in everyday life, unmistakable when you zoom in. And the irony is that Planck, who resisted probability early in his career, ended up helping create a physics where probability is fundamental. The universe did not become less lawful because of quantum theory, but the laws became different from what classical intuition had promised. They became laws of distributions, amplitudes, and constraints on what can be known simultaneously. Planck's act of quantization was one of the first cracks in the classical wall. The wall did not collapse all at once. It cracked, and then it cracked again, until an entirely new structure had to be built. You have been listening to Scientific Giants Who Changed the World. Today we stood beside Max Planck as he tried to fix blackbody radiation and ended up quantizing energy, setting a constant into the foundations of nature, and launching a revolution he never fully trusted. In our next episode, we will meet Niels Bohr, the architect of the quantum atom, whose model and whose philosophical insistence on complementarity would change not only physics, but what it means to describe reality at all. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear, because the quantum revolution begins not with a list of postulates, but with a human being facing a stubborn curve and choosing honesty over comfort. Until our next hour together, remember, sometimes the smallest assumption is the hinge on which an entire century turns.